Good morning, students. Welcome to Bindu Dhadwal Chemistry Lessons. Today we'll be doing alkynes topic of the chapter Hydrocarbons of your book. So, alkynes are unsaturated compounds containing a triple bond. The general formula of alkynes is CnH2n minus 2. So, alkynes, because they have two pi bonds, will have 4 hydrogens less than alkanes, which have the general formula CnH2n plus 2, and 2 hydrogens less than alkenes, which have the general formula CnH2n. So alkynes have general formula CnH2n minus 2. The first member of this family, ethyne, is also called acetylene in common system. It is used for welding purposes by mixing with oxygen. Oxyacetylene flame produces so much heat that you can weld 2 iron pieces together. Ethyne plus oxygen or acetylene plus oxygen forms oxyacetylene, which is used for welding purposes. It is also the starting material for many organic compounds. Nomenclature of alkynes, we can name them by 2 methods. In common system, we can name them as derivatives of acetylene. So CH, triple bond CH is acetylene. This compound will be called, because this is acetylene, methyl acetylene. This will be called, this is acetylene, ethyl acetylene. This will be called, this is 2 carbon compound. This will be called dimethyl acetylene. In IUPAC system, they are named as derivatives of alkanes. You remove the suffix "ane" from alkenes and add the suffix "ine" to name the compound. For example, an alkyne with 3 carbon atoms will be called propyne. A 3 carbon alkane is called propane. So propane minus ane plus ine. Minus ane plus ine makes it propyne. Then similarly, a 4 carbon compound will be called butene, because the triple bond is at first carbon atom, so it will be called but1-ine. This will be called but2-ine. If we number, the triple bond starts from second carbon, so name is but2-ine. Similarly, while naming of the compounds, the longest continuous carbon chain containing the unsaturated bond, triple bond, is selected. Numbering is started from that end which is closest to the triple bond, and once we have numbered, then we will name the prefix first, and we will also explain its position. So as it is attached to carbon number 3, so it will be called 3-methyl pent for 5 carbons and 1-ine for triple bond. So triple bond is at carbon atom number 1, so name will be 3-methyl pent 1-ine. This is how naming is done. Similarly, in this compound, numbering starts from here and carbon is attached, substituent is attached, methyl at position number 4. So name will be 4-methyl pent 1-ine. In alkynes, when the molecular formula is same but the structural formula is different, the properties are different, this process phenomena is called isomerism, and alkynes will show position isomerism as well as chain isomerism. Let us see the structures of different isomers of C5h8 pentyne. So we can write different structures. One structure will be of 5 carbon atoms and triple bond at first position, then another of 5 carbons, triple bond at second position. Then we can have a 4 carbon chain with a substituent at the third position, while the triple bond is at the first position, and this isomer will be called Pent1-ine, Pent2-ine. This is 3-methyl-but1-ine. These are different isomers of C5H8. Now, this first and this third structure, these isomers are called chain isomers because difference arises on the types of a chain. This is a 5-chained compound, 5-membered chain. This is a chain of 4 carbon atoms with 5th carbon as a substituent. And similarly, these two will be position isomers because here the difference arises on the position of the triple bond. The triple bond is at first carbon in this chain and at second carbon in this chain. Similarly, for hexynes, we can have these isomers, a chain of 6 carbon atoms with triple bond at the first carbon, chain of 6 with triple bond at the second carbon, chain of 6 with triple bond at the third carbon, then chain of 5 with a substituent methyl at third carbon or at the fourth carbon. Then we can also have a chain of 4 with 2 methyls at the third carbons. So the different names will be, this is hex1-ine, hex2-ine, hex3-ine. This is, we start the numbering from this end. So this is 3-methyl-pent1-ine. This will be 1, 2, 3, 4. 4-methyl-pent1-ine. This compound with the triple bond at the second carbon atom and methyl group at the fourth will be 4-methyl-pent2-ine. Then we can have a 4-chain. So structure 1, 2, 3. So 3,3-dimethyl-but1-ine. So these are the different isomers of the formula C6H12 minus 2 is 10. C6H10. Now, structure of triple bond. So when there's a triple, let us do the structure of a simplest alkyne, Ethyne. So in Ethyne, the carbon atoms where the triple bond is placed is sp hybridized. So there are 2 sp hybrid orbitals. One sp hybrid orbital of this carbon atom will form a sigma bond with a sp hybrid orbital of the other carbon atom, and the second sp hybrid orbital will overlap with the 1s orbital of hydrogen atom to form a sigma bond. So here we show the sigma bonds of Ethyne. Then in the second diagram, we will show the pi bonds. So the same carbon atom has 2 p orbitals which are unhybridized. This is 2px orbital, this is 2py orbital. So 2px orbital, 2px unhybridized orbital of one carbon atom will sidewise overlap with the 2px unhybridized orbital of other carbon atom to form a pi bond. Similarly, 2py will combine with 2py. The structure is such that 2py is in the plane of the paper and 2px is above the plane of the paper. So in case of Ethyne, there is one carbon-carbon sigma bond, single bond, and out of the 3 bonds, 2 are pi bonds. So this is the structure. 2 carbon-carbon sigma bonds and 2 bonds will be carbon-hydrogen sigma bonds and 2 bonds will be carbon-carbon pi bonds. And the bond length of carbon-carbon triple bond is 120 picometer, which is shorter than double bond, which is 133 picometer, and which is still shorter than single bond, which is 154 picometer in alkenes. The bond enthalpy of triple bond is greater than that of double bond, 823 kilojoules. For double bond it's 681, for single bond it is 348. So triple bond is most difficult to break. Out of the 3 bonds, the pi bonds are easier to break than the sigma bond. So this is the structure of the triple bond in case of Ethyne. Preparation of alkynes. So we can prepare from calcium carbide, and this method of preparation from calcium carbide is industrial method of preparation. We prepare alkynes in large amounts by this method. So alkyne is prepared by treatment of calcium carbide with water. Water is treated with calcium carbide to form calcium hydroxide and ethyne or acetylene. The calcium carbide needed for this purpose is prepared from quicklime. So quicklime is heated with coke, and we get calcium carbide and carbon monoxide. Now the quicklime needed for this method is prepared from limestone by heating it. On heating calcium carbonate, we get calcium oxide and carbon dioxide. Calcium oxide on heating with coke will give calcium carbide. Calcium carbide on treating with water will give ethyne gas. From vicinal dihalides also we can prepare alkynes. So this is a vicinal dihalide, means halogen atoms are present at two adjacent carbon atoms. So if we reacted with alcoholic KOH, that is reacted with KOH in presence of alcohol, it will cause elimination. First one H and one Br of adjacent molecule will combine to form HBr. This HBr will react with KOH to form KBr, and a double bond, because H and Br are removed, a double bond is formed here. So Br of this carbon atom and H is removed, HBr, so CH2 is left here and CHBr is left here. So what we get is CH2 double bond CH Br. Then in the next step, after heating with alcoholic KOH, we get ethylene bromide. Then we reacted with sodamide. So this Br of alkynyl bromide will react with Na of sodamide to form NaBr. So NaBr is removed. Also NH2 will combine with this H to form NH3. So NaBr and NH3 are eliminated, and when these move out, another bond is formed. So from double it gets converted to triple bond and ethyne is formed. So by carrying out elimination twice from vicinal dihalides, we can prepare alkynes. For example, in this case we have prepared ethyne. Properties. The first physical properties, first three members are gases, next 8 are liquids, and higher ones are solids. All alkynes are colorless. Ethyne is colorless but has characteristic odor. Other members are odorless. Alkynes are weakly polar in nature. Carbon having sp hybridization is electronegative and attracts the electrons towards itself, thereby causing a dipolarity. It's a polar bond. This is negatively charged, this is positively charged. These alkynes are lighter than water and immiscible with water also. But they are stable in organic solvents. They will dissolve in organic solvents like ether, CCl4 and benzene. The melting point, the boiling point, the density will all increase with the increase in molar mass, because forces of attraction increase with the increase in molar mass. Chemical properties of alkynes. First is acidic character of alkyne. Acidic character can be seen because alkynes react with basic substances like sodium metal or sodamide. These basic substances will react with ethyne to liberate hydrogen gas, just like acids liberate with basic substances to form hydrogen gas. Alkynes are acidic. Alkanes and alkenes are not. This is because in alkynes the carbon atoms are sp hybridized. They have 50% s character, because of which they have highest electronegativity and attract the shared pair of electrons toward themselves. As a result, this bond is weak and more towards carbon, and the release of proton is easier, so they are acidic in nature. The hydrogen which is attached to triply bonded carbon will be acidic in nature. The sp2 hybridized carbon of ethene has 33% s character, less than sp hybridized, and so it is less electronegative. End sp3 has 25% S character, which is less acidic than alkene. This is less acidic than alkyne. So alkynes are most acidic in nature. So alkyne will react with basic substance like sodium to form sodium acetylide and release hydrogen gas. This happens with the other hydrogen atom also. So first monosodium ethynide ion will be formed with the release of hydrogen gas. Then this will further react with sodium metal to give this also as hydrogen gas, whereas propyne will give only monosodium propionite. And these reactions will not be shown by alkenes and alkanes. So we can use them to distinguish between alkynes, alkenes and alkanes. Now, out of the three, alkyne will be most acidic, then alkene, then alkane. And with respect to carbon atoms, 2 carbon atom alkyne, ethyne will be most acidic in nature, than propyne, then butane. Addition reactions. Alkynes have triple bond, so the pi bonds can be broken, and whenever a pi bond breaks, some substance can be added to it. For example, because there are 2 bonds, 2 molecules can be added. For example, hydrogen can be added, halogen can be added, and hydrogen halide can also be added. And the formation of addition product will take place. First, hydrogen will be added. The pi electrons move to one of the carbon atoms. This becomes negatively charged, this becomes positively charged. The positively charged H goes to the negatively charged carbon and gets attached here, whereas the positive charge is left on the other carbon atom. This cation is vinylic cation. Now the product is formed with respect to stability. That cation will be formed which will be more stable, and then in the second step, the negatively charged nucleophile will get attached on the positively charged carbon atom to form this addition product. The addition product formed will depend upon the stability of vinylic cation. Now, whenever addition takes place to unsymmetrical alkyne, it will take place according to Markovnikov's rule. That is, the negative part of the adding molecule will go to that carbon atom which contains less number of hydrogen atoms. Majority of reactions of alkynes are examples of electrophilic addition reactions. That is, the positively charged electrophile is added first and then followed by addition of nucleophile. Addition of dihydrogen, when alkyne is treated with hydrogen in presence of a catalyst like platinum or palladium or nickel, this bond will break. One hydrogen will get attached here, one here to form ethene. Because there is still one weak pi bond, another hydrogen can be added to form ultimately ethane. Similarly, when hydrogen is added to propyne, first propene will be formed and then propane will be formed. The catalyst used can be platinum or palladium or nickel. On addition of halogens, again one bond will break, one Br will be attached here, one Br here. So we get a double bonded dibromo product. This will further add another molecule of bromine, another bond will break and another bromine will be added to form tetrabromo substituted alkene with single bond. Because bromine is reddish orange in color, when it gets added to alkyne, this color is removed. It is decolorized. So this test can be used as a test for unsaturation. That is, any compound containing a double or a triple bond, when it reacts with bromine dissolved in carbon tetrachloride, the bromine solution will get decolorized. If it gets decolorized, it means unsaturation is present, double or triple bond is present. In case of addition of hydrogen halide, 2 molecules will be added. First, the bond will break, one H and Br is added to form a double bonded compound, then bond breaks and again another H is added to this side and Br to this side to form a 1,1 dibromo ethane product. Similarly, in case of propyne, Br will be added to carbon having less hydrogens, so one Br gets attached here. Triple bond breaks to double bond and then double will break to single bond, and both the pairs will be attached to carbon atom containing less hydrogen. So 2,2-dibromopropane is formed. Addition of water. One molecule of water adds up to ethyne in presence of mercuric sulfate and dilute sulfuric acid at 333 Kelvin to form first enol, double bond, and OH. First, this product will be added. This is Markovnikov's addition. Hydrogen will go to that negative part. OH will go to that carbon which contains less hydrogens. This is symmetrical. We will see in unsymmetrical that it goes to that carbon which has less number of hydrogen atoms. This enol then isomerizes itself. The double bond will go to this bond and H will move to this carbon to form CH3, C double bond O. Aldehyde will be formed. In case of propyne, when this bond breaks, OH is added here, H is added here, and double bond is there. So this is an ene for double bond and ol for OH. It will isomerize itself to ketone. The double bond goes here and H goes here to form CH3, C double bond O, single bond CH3. Propanone or acetone in common system is formed. Polymerization. In case of linear polymerization under suitable conditions, ethyne will add up. So one bond will break. This is triple bond. This bond breaks. So two valencies are freed. So triple bond will get converted to CH2, double bond CH2. From this side, it gets added to another alkyne molecule. From this side, it gets attached to another alkyne molecule. Again, in the same manner, that is, one bond is broken. So this group will be repeated again and again. This will be the repeating unit, and it can be represented as this n times CH double bond CH, single bond CH, double bond CH, n times. So polymer is formed. So the important characteristic of this polymer is that under special conditions it will conduct electricity. So a thin film of polyacetylene can be used as electrodes in batteries, and they are not only good conductors, they are lighter in weight and cheaper than the metal conductors. These alkyne molecules can also polymerize in a cyclic manner. 3 molecules of ethyne, when passed through a red hot iron tube at a temperature of 873 Kelvin, will join with each other. One of the bond will break and form bond between adjacent acetylene molecules. These electrons form bond here, these electrons form bond here, these electrons form bond here to form single bond, double bond, single bond, double bond structure, which is called benzene. This benzene is the starting molecule for preparation of derivatives of benzenes. It can be used for making dyes, it can be used for making drugs, a large number of organic compounds, and this method is the best method for converting an aliphatic compound into an aromatic compound. So just revising how we can convert ethanoic acid into benzene. In the process, we will revise many of the reactions of alkenes, alkenes, and alkynes. So let us convert ethanoic acid to benzene. So we can convert ethanoic acid. We will heat it with sodium hydroxide aqueous solution to form sodium acetate. Sodium acetate, when heated with soda lime, soda lime is a 3:1 mixture of sodium hydroxide and calcium oxide. When heated with it, 1 carbon less alkane is formed. So 2 carbon compound will change into 1 carbon alkane. When heated with chlorine in the presence of ultraviolet radiation, chlorination occurs. H is replaced by Cl to form CH3Cl. This, on heating with sodium in presence of dry ether, undergoes Wood's reaction to convert double the number of carbon atoms alkane. So alkane of 2 carbons is formed from alkyl halide of 1 carbon. This alkane, when we will carry out its chlorination, we can form ethyl chloride. H is substituted by Cl. This, on reaction with alcoholic KOH, will undergo elimination. 1 H and 1 Cl will be removed to form a double bond here. That HCl will react with KOH to form KCl and water. So minus KCl and minus water, and this gets converted to alkene. When we add bromine to it, the bond will break and Br will be added here and here. So when this dibromoethane is formed, we reacted with alcoholic KOH to again carry out its elimination. This time 1H and Br will be removed to form a double bond and alkynyl bromide. This on reaction with NaNH2 soda might will another H and another Br will be removed and acetylene will be formed. Acetylene on passing through red hot iron tube at a temperature of 873 Kelvin will undergo cyclic polymerization to form benzene. So this is the flow chart for converting ethanoic acid ultimately to benzene. That's all in this video. If you like the video, please do share and subscribe. Thank you. Have a nice day.